You see two dice roll. One lands on 6, the other, 1,000 kilometers away, lands on 1. Perfect opposites, every time. Not because someone rigged them, not because they communicated, because at some point before you separated them, they became entangled, and now measuring one instantly determines the other, regardless of the distance between them. Einstein called it spooky action at a distance. He hated it. Thought it proved quantum mechanics was incomplete. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, published a paper asking if quantum mechanical description of physical reality could be considered complete. The paper, known as EPR, was meant to demolish quantum theory. Instead, it opened the door to the second quantum revolution. What happens when you measure one particle and instantly know the state of another particle light years away? How fast does entanglement actually occur? What connects these particles across the void? And why does every experiment confirm the universe operates in a way Einstein insisted was impossible? Podolsky wrote it. Einstein complained later that the essential thing was smothered by formalism. The paper described two particles that interact and then separate. Measure the position of one, and you instantly know the position of the other. Measure the momentum of one, and you know the momentum of the other, without touching the second particle. Einstein, Podolsky, and Rosen argued this meant quantum mechanics was incomplete, that particles must carry hidden variables, predetermined properties that explain the correlations without faster-than-light influence. They ended the paper saying, quantum theory does not provide a complete description of physical reality, but they believed such a theory was possible. Einstein was furious. He wrote to the Times saying any information upon which the article was based was given without authority. It remains his invariable practice to discuss scientific matters only in the appropriate forum. He deprecated advanced publication in the secular press. Physicist Edward Condon, asked for comment, said a great deal of the argument hinges on just what meaning is to be attached to the word reality in physics. Max Jammer later noted, it remains a historical fact that the earliest criticism of the EPR paper, moreover, a criticism that correctly saw in Einstein's conception of physical reality the key problem of the whole issue, appeared in a daily newspaper prior to the publication of the criticized paper itself. He introduced the term entanglement, or Verschränkung in German, to describe the EPR scenario. Schrödinger wrote that entanglement is not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. He was dissatisfied with it. Like Einstein, it seemed to violate the speed limit on transmission of information implicit in relativity. Einstein later called it spooky action at a distance. The phrase stuck. Schrödinger's cat paradox, usually cited for the measurement problem, originated in this correspondence. September 19th, 1935. Schrödinger told Einstein he had constructed an example very similar to Einstein's exploding powder keg, and he outlined the cat. A cat in a box with a radioactive atom, a Geiger counter, a hammer, and poison. If the atom decays, the hammer breaks the vial, the cat dies. Until you open the box, quantum mechanics says the cat is in a superposition of alive and dead. Schrödinger used it to argue for incompleteness without assuming separability and locality. Also, this script is researched and factual, using sources from Physical Review Letters, the journal that published the original EPR paper in 1935, and the Vienna University of Technology's Atosecond entanglement measurements, published October 24, 2024, along with Nature Communications' Teleportation experiments from November 18, 2025. These are peer-reviewed primary sources, not popular science summaries. Now back to the information. Entanglement entered physics, but no one knew if it was real or just mathematics. John Stuart Bell changed that. 1964. Bell, working at CERN, published a paper showing that if local hidden variables exist, if particles carry predetermined properties independent of measurement, then certain statistical correlations must be limited. He derived inequalities, mathematical constraints. If experiments violate these inequalities, local realism is wrong, quantum mechanics is right, and particles genuinely are connected across space in ways that defy classical physics. More practical for experiments, easier to measure with photons. Clauser wanted to test it. His graduate advisor told him it was a waste of time. Clauser wrote to Bell anyway. Bell confirmed no experiment had been done and encouraged him. Clauser started planning. He needed entangled photons. He needed polarizers. He needed detectors sensitive enough to measure correlations. Stuart Friedman joined him. They built the apparatus at UC Berkeley. 1972. They used calcium atoms excited by ultraviolet light. The atoms emitted pairs of photons in a cascade. The photons were entangled in polarization. Clauser and Friedman measured correlations at different polarizer angles. The results violated Bell's inequality by more than 4 standard deviations. Quantum mechanics was right. Local hidden variables were wrong, but there were loopholes. Detection efficiency was low. Not all photon pairs were detected. Maybe the detected pairs were biased, the fair sampling loophole. Aspect realized why it was interesting and why it was hard. The topic was still viewed with skepticism. Bell himself, at a discussion at CERN, recommended Aspect pursue it only if he had a permanent job. Aspect did, a teaching position. Between 1981 and 1982, Aspect and his team, Philippe Grangier, Jean Delaborde, and Gérard Roget, performed 3 experiments at the Institut d'Optique d'Orsay. They improved the source, used a 2-photon laser excitation of atomic radiative cascades in calcium, dramatically better than previous sources. First test, they excited calcium atoms more efficiently, boosting pair production. Second test, they used polarizing cubes that transmit one polarization and reflect the other rather than blocking it. They could measure photons with both polarizations. Detection efficiency improved. Third test, the breakthrough. In Clauser's setup, the polarizers stayed at fixed angles for long periods. The locality loophole, information about one polarizer's orientation could travel at light speed or slower and still reach the other side before photons were detected. Aspect's team switched polarizers rapidly during photon flight. They used acousto-optic modulators, switching time, 10 nanoseconds. Flight time between detectors, 40 nanoseconds. No time for light speed signals to coordinate. The experiment was published in Physical Review Letters, December 1982. It violated Bell's inequality by more than 40 standard deviations. The quantum mechanical prediction matched the data. Local hidden variables were ruled out. Aspect's work was a turning point. The physics community began to take entanglement seriously. Not just a curiosity, a real phenomenon with technological potential. They violated the CHSH inequality by over 30 standard deviations. Coincidence curves agreed perfectly with quantum theory. Same year, a team in Geneva tested entanglement over 30 kilometers of optical fiber in the Swiss telecommunications network. They used atomic clocks to timestamp measurements. The violation of Bell's inequality was verified again. If a hypothetical coordination signal existed, it would have to travel 10 million times the speed of light. Not plausible. Quantum mechanics was confirmed beyond any reasonable doubt. 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The prize recognized decades of work proving Einstein wrong about spooky action at a distance. Entanglement is real. Particles genuinely are connected in ways that defy local realism. You perform a Bell state measurement on the third particle, and Alice. The measurement entangles them and collapses both states. The outcome of the measurement is sent classically to Bob. Bob applies a correction based on the outcome. Now Bob's particle is in the same state the third particle started in. The original state is destroyed. The teleported state appears at Bob's location. Information isn't transmitted faster than light. The classical outcome must travel from Alice to Bob, but the quantum state is transferred without being measured. A team teleported photon states across 143 kilometers of open air in the Canary Islands between 2 astronomical observatories, record for ground-based teleportation. 2017, the Chinese MICUS satellite, launched 2016, teleported quantum states from the ground in Tibet to the satellite in orbit. Distance, 500 to 1,400 kilometers depending on satellite position. The photon beam was fired from a ground station carrying an entangled photon. They entangled it with a third photon on the ground, measured their states, and the state appeared on the satellite. Jigang Ren at the University of Science and Technology in Shanghai led the team. The experiment shattered distance records. Quantum teleportation works across space. Prem Kumar's team at Northwestern University demonstrated quantum teleportation over busy internet cables. 30.2 kilometers of fiber optic cable carrying live classical traffic. Millions of photons for internet data. Single photons for quantum teleportation. Kumar's team studied how light scatters in fiber. They found a less crowded wavelength, placed the quantum photons there, used filters to reduce noise. It worked. Teleportation coexisted with classical communications, published in Optica. The result means quantum networks can use existing infrastructure. No need to build separate dedicated cables. If you choose wavelengths properly, classical and quantum can coexist. Quantum dots. First time ever. Quantum dots are semiconductor nanostructures that emit photons. Each dot's photons are slightly different in frequency and timing. Hard to make them indistinguishable. The Stuttgart team developed quantum dots that generate nearly identical photons. They used frequency converters developed by Christoph Becker's group at Saarland University to compensate for residual differences. They separated the quantum dots by 10 meters of optical fiber. Teleportation success rate, over 70%, published in Nature Communications. The team aims to extend this to longer distances. Previous work showed entanglement from quantum dots survives 36 kilometers through Stuttgart city center. Quantum repeaters, which renew quantum information before it degrades, depend on teleporting information between distant sources. This experiment is a critical step toward building a quantum internet. February 25, 2025. Researchers at Oxford University used teleportation to link two physically separate quantum processors and performed a logic gate across machines. Not just sending information, computing with it. 3 breakthroughs in 4 months. Northwestern showed teleportation works on live internet cables. Oxford showed it can perform computation between processors. Illinois showed it can be miniaturized on chips. These aren't separate projects. They're pieces of the same infrastructure puzzle. Combine them, and you have the foundation for a quantum internet. The sender and receiver detect the disturbance, the key is compromised. They discard it and try again. Unbreakable encryption, guaranteed by quantum mechanics. 1989. Bennett and Broussard demonstrated BB84 over 32 centimeters. 2007. A team sent quantum encrypted data over 200 kilometers of fiber between Geneva and Bern, Switzerland. Commercial quantum key distribution networks now operate in China, Europe, and the United States. The Chinese MIXUS satellite enables quantum encrypted communication between ground stations thousands of kilometers apart. Encryption relies on entanglement. If the particles aren't entangled properly, the key doesn't work. When you entangle multiple qubits, you create superpositions of exponentially many states. 2 qubits, 4 states, 3 qubits, 8 states, 50 qubits, over 1 quadrillion states. A quantum computer with 50 entangled qubits can represent more states simultaneously than there are atoms in the solar system. Entanglement is the resource that gives quantum computers their power. Without it, they're just classical computers. Shor's algorithm for factoring large numbers depends on entanglement. Grover's algorithm for searching databases depends on entanglement. Every proposed quantum advantage depends on creating, maintaining, and manipulating entangled qubits. But entanglement is fragile. Interaction with the environment destroys it. Decoherence. The qubits become disentangled. The quantum computer collapses to classical behavior. Current quantum computers operate at millikelvin temperatures in shielded chambers to minimize decoherence. Entanglement must be protected. Norman Yau and Maxwell Bloch at Harvard published research in Nature Physics on spin squeezing, a type of entanglement that reshapes measurement uncertainty. Instead of a circle of uncertainty, you get an ellipse. Squeeze the uncertainty in one direction, and it expands in the perpendicular direction. Use entangled particles, and you can measure certain quantities more precisely than classical systems allow. Quantum-enhanced metrology. Applications in atomic clocks, gravitational wave detectors, magnetic field sensors, nitrogen vacancy centers in diamond. These are defects in diamond's crystal structure. They can be entangled. They're extremely sensitive to magnetic fields. Medical imaging, material science. November 11th, 2025, UC Santa Barbara physicists engineered entangled spin systems in diamond that surpass classical sensing limits through quantum squeezing. Published results showing next-generation quantum sensors are feasible. A team at TU Wien in Vienna, led by Joachim Burgdorfer and Iva Brzezinova, published research in Physical Review Letters showing entanglement is not instantaneous. It happens on attosecond timescales. An attosecond is a billionth of a second, 1 quintillionth of a second. Light travels the width of a human hair in 1 attosecond. Atom with 2 electrons. 1 electron gets ripped out, the other stays but jumps to a higher energy state. The 2 electrons become entangled, but not instantly. The electron doesn't just jump out of the atom. It's a wave that spills out, so to speak. That takes time. During that phase, the entanglement occurs. The birth time of the escaping electron is quantum entangled with the energy state of the remaining electron. If the remaining electron is in a higher energy state, the escaping electron likely left earlier. If it's in a lower energy state, the escaping electron likely left later. The difference averages 232 attoseconds. The electron itself doesn't know when it left the atom. It's in a quantum superposition of different departure times. The measurement protocol combines 2 laser beams, attosecond streaking, rabbit technique, reconstruction of attosecond beating by interference of 2 photon transitions. The team showed these differences can be calculated and measured. They're already in talks with experimental groups to verify the predictions in the lab. Also, this script is researched and factual using sources from Nature Journals, January 8th, 2024. Publication on entanglement and topology by the University of the Witwatersrand, along with the February 10th, 2025 Kyoto University breakthrough on W-state entangled measurement published in their official release. These are institutions at the cutting edge of quantum research, not clickbait tech blogs. Now back to the information. Skyrmions in magnetic materials and liquid crystals are stable, resistant to noise. The team showed quantum entanglement can carry topological properties. The entanglement is malleable, like clay, but during transformation, certain topological features remain constant, like a coffee mug morphing into a donut. The shape changes. The whole remains, topological invariant. The researchers created entangled photon pairs where the entanglement itself has topological structure. The entanglement is non-local, shared between spatially separated particles. Previous work treated skyrmions as localized at a single location. This work shows topology can be non-local, distributed across entangled systems. They propose using topology as a framework to classify entangled states, like an alphabet, a labeling system. Different topological structures correspond to different types of entanglement, useful for quantum communication, quantum computing. Isaac Nape, a co-investigator, says this fresh perspective can serve as a classification scheme. High-density data storage uses magnetic skyrmions for stability. Quantum entangled skyrmions could have similar transformative impact. A team at Technion in Israel discovered a new type of quantum entanglement, published in Nature. First discovery of a new quantum entanglement in more than 20 years. The team entangled the total angular momentum of photons confined in nanoscale structures. Angular momentum has two components, spin and orbit. Spin relates to the photon's rotation of the electric field. Orbit relates to the photon's rotational motion in space. Previous entanglement involved one or the other. This work entangles both simultaneously in the total angular momentum, near-field photon entanglement. The photons are confined in nanometric systems. The discovery opens pathways for miniaturizing quantum communication and computing components. Photon-based quantum devices have been bulky. This allows shrinking them to nanoscale, integration on chips. The Technion team includes researchers who studied with Nathan Rosen, one of the original EPR authors. Rosen later founded the Faculty of Physics at Technion. The connection to EPR is direct. The W state is one of two representative types of multiphoton entanglement. The other is the Greenberger-Horn-Zeilinger, or GHZ state. Entangled measurement of GHZ states was realized years ago. W state measurement had never been proposed or demonstrated experimentally. The W state has cyclic shift symmetry. The team exploited this to design a measurement using photonic quantum circuits. They built a device with high stability optical circuits that operate without active control for extended periods. 3 single photons, inserted in appropriate polarization states, are distinguished by the device into different types of 3-photon W states. Each corresponds to a specific, non-classical correlation between the 3 input photons. The team evaluated fidelity, the probability of obtaining the correct result for a pure W state input. This achievement opens the door for quantum teleportation of W states, new quantum communication protocols, transfer of multiphoton entangled states, new methods for measurement-based quantum computing. More than 25 years after entangled measurement for GHZ states was proposed, they finally obtained entangled measurement for the W state with genuine experimental demonstration. For a long time, understanding of entanglement was built upon idealized assumptions. The work shows fundamental discrepancies arise in key quantum computing measurements when performed under realistic, which is to say efficient, conditions. The team introduced 2 key figures, computational distillable entanglement and computational entanglement cost. These quantify rates of entanglement in quantum states in the form of entangled bits, or EBITs, within restricted conditions. The research suggests that achieving perfect entanglement manipulation in laboratory settings is harder than physicists assumed. This doesn't invalidate entanglement. It clarifies practical limits on how it can be used. Realistic quantum computers will face constraints. Understanding those constraints is essential for building functional machines. Does quantum entanglement have a similar second law? Can entanglement transformations be made reversible? The difficulty is that entanglement is far more complex than thermodynamic systems. The team used probabilistic calculations. They showed that reversibility is achievable in entanglement theory under certain conditions. This is the first evidence that reversibility can apply to quantum entanglement. Stronger forms of reversibility have been conjectured. Can entanglement be made reversible without probabilistic transformations? That remains an open problem. Answering these questions requires solving mathematical and information theoretic problems that have evaded all attempts so far. Understanding the requirements for reversibility remains a fascinating challenge. But the work establishes that entanglement, like thermodynamics, may have fundamental laws governing its transformation and use. The Poincare sphere represents polarization states. Due to quantum entanglement between idler photons and structured signal photons, the evolution path of idler photons on the fundamental Poincare sphere can be non-locally mirrored by structured signal photons on higher-order Poincare spheres, resulting in quantum path entanglement. Non-commutative metasurfaces enable switching diverse quantum path entanglement across different higher-order Poincare spheres using distinct combination sequences. Metasurfaces are nanostructured layers, thin, compact. Replace bulky optical components, quantum computing, quantum communication. This work shows metasurfaces can manipulate quantum entanglement in novel ways, tuning across a broad spectrum of quantum states. Significant advancement in manipulation of quantum entanglement. A team demonstrated a new way of entangling light and sound, prerequisite for secure quantum communications and quantum computing. acoustic phonons, optical photons, entangling different physical systems. Hybrid entanglement expands the toolbox for quantum technologies. Different systems have different advantages. Photons for long-distance communication, phonons for local processing. Entangling them bridges the gap. September 2nd, 2025, scientists in Japan uncovered strange behavior in heavy electrons that act as if they carry far more mass than usual. They found these heavy electrons are entangled. Published findings: heavy fermion systems, condensed matter physics, entanglement at play in materials previously thought to be classical, quantum effects in solids. Future of quantum computing may involve materials where electrons are naturally entangled, not isolated qubits, bulk materials with intrinsic quantum properties. Most quantum satellites create entangled pairs in space and send each half down to Earth. Downlink, used for cryptography. Few photons needed. Uplink is harder, sending photons from Earth to space. Atmosphere scatters them, turbulence, clouds. But uplink is necessary for practical quantum networks. The team modeled it, showed it's possible with current technology. The Jinan-1 microsatellite in 2025 established a 12,900 kilometer quantum connection between China and South Africa. Quantum entanglement as a commodity, like electricity, generated and transmitted invisibly. Quantum devices plug into an entanglement source and a power source, both essential. The vision is long-term, but the groundwork is being laid. A study published in Nature by Joseph Aziz and colleagues complicated efforts to test whether gravity is quantum. Richard Feynman proposed an experiment in 1957. If gravity can entangle two massive objects, it would indicate quantum behavior. The experiment wasn't feasible then. Technology is approaching the point where it could be. But the new study shows classical theories of gravity can also produce entanglement. It's not just quantum gravity. Classical gravity plus quantum field theory for matter can generate entanglement via different mechanisms. Observing entanglement alone doesn't unambiguously indicate quantum gravity. The strength of entanglement depends on parameters, mass, duration. Whether the effect is quantum or classical may still be discernible, but the finding complicates interpretation. Physicists working on testing quantum gravity will need to carefully design experiments to distinguish between classical and quantum sources of entanglement. Quantum computers solving problems classical machines can't touch. Drug discovery, materials design, optimization, climate modeling, quantum sensors detecting gravitational waves, mapping magnetic fields in the brain, finding ore deposits underground. Entanglement powers all of it. The experiments proving it exists were considered fringe science for decades. Now they're Nobel Prize-winning work. The infrastructure to use it is being built. Satellites, fiber networks, quantum repeaters, chips. Because the particles were never truly separate. They're described by a single shared wave function. Entanglement is the defining feature of quantum mechanics, the trait that separates it from all classical physics. They demonstrated that entangled particle pairs considered by EPR could be observed experimentally. 1957. David Bohm and Yakir Aharonov showed the results of Wu and Shaknoff already demonstrated entanglement of photon pairs. First confirmation of entanglement predated Bell's work. 1964. Bell formalized the test. 1972. Clauser and Friedman did the experiment. 1982. Aspect closed loopholes. 1997. Zeilinger teleported quantum states. 2016. Makeshift's satellite extended entanglement to space. 2022. Nobel Prize. 2024. Teleportation over internet cables. 2025. W state measurement. New types of entanglement discovered, Atosecond timing measured, quantum internet infrastructure rolling out. The universe operates on entanglement, not just in labs, everywhere. Photosynthesis. Birds navigate using quantum entanglement in their eyes. Cryptochromes, proteins sensitive to Earth's magnetic field, use entangled electron pairs. Quantum biology, enzyme reactions, DNA mutations, olfaction. Smell might rely on quantum tunneling and entanglement. Controversial, not settled, but possible. At the most fundamental level, particles in the universe have been interacting since the Big Bang. Everything is entangled with everything else to some degree. We don't notice because decoherence is fast. The environment constantly measures quantum systems, collapsing superpositions, disentangling particles. But before decoherence, entanglement is there, subtle, pervasive. The quantum substrate underlying reality. Entanglement allows no local hidden variables. Particles don't carry predetermined properties. The measurement outcome depends on the entire entangled system. You can't describe one particle without the other. Einstein's realism, the idea that particles have objective properties independent of observation, doesn't hold. Quantum mechanics forces us to accept that measurement is fundamental, not just revealing pre-existing properties, creating them. The observer is not separate from the observed. Measurement disturbs the system, changes it. In entangled systems, measuring one particle changes the other, instantaneously. Across any distance, no signal propagates, no cause and effect chain. The correlation is built into the wave function from the start. Measuring collapses it. Both particles simultaneously snap into definite states that are correlated. EPR argued this was absurd. It violated locality. If no signal travels, how does one particle know what happened to the other? They concluded quantum mechanics was incomplete. Hidden variables must exist. Bell proved hidden variables can't reproduce quantum predictions unless they're non-local. Experiments confirmed quantum predictions. Therefore, non-local correlations exist. Spooky action at a distance is real, but it's not action. It's correlation. You can't use it to send messages faster than light. The outcome of measuring one particle is random. You learn the outcome of the other particle's measurement, but you can't control it. No communication, no violation of relativity. Just correlation. Stronger than any classical correlation. Strong enough to violate Bell's inequality. Strong enough to power quantum computers. China has a 2,000-kilometer quantum communication line between Beijing and Shanghai. 32 trusted nodes. Quantum encrypted data transmission. European Quantum Communication Infrastructure Project aims to link quantum networks across the EU. United States has quantum networks connecting national labs. Private companies are building quantum internet test beds. Amazon Bracket, IBM Quantum Network, Google Quantum AI, Microsoft Azure Quantum. Startups developing quantum repeaters, quantum memories, quantum transducers. The pieces are coming together. Within a decade, quantum internet will be real. Entanglement distributed on demand, qubits teleported between quantum computers, secure communication guaranteed by physics, not mathematics. Atmosphere scatters them. Detectors have finite efficiency. Quantum repeaters need quantum memories to store entangled states while waiting for confirmation signals. Quantum memories must have long coherence times, seconds, minutes. Current memories lose coherence in milliseconds. Progress is being made. Rare earth ions and crystals, cold atomic ensembles, nitrogen vacancy centers. Each system has trade-offs, storage time, efficiency, wavelength compatibility. No single solution yet dominates. Research continues. Scaling is hard. Entangling 2 qubits is easy. Entangling 50 qubits is exponentially harder. Error rates increase. Decoherence accelerates. Quantum error correction is necessary. But error correction requires redundancy. Multiple physical qubits per logical qubit. Overhead is massive. Current quantum computers have tens to hundreds of physical qubits. Fault-tolerant quantum computers need millions. Orders of magnitude improvement needed. Google's Willow chip, announced December 2024, showed progress on error correction. More qubits, lower error rates, but still far from practical fault tolerance. Simulating quantum systems, chemistry, materials, science, drug design, factoring large numbers, breaking RSA encryption, searching unsorted databases faster than any classical algorithm, optimization problems, machine learning, artificial intelligence, climate modeling, financial modeling, logistics. Every field that relies on computation could be transformed. The race is on. Countries invest billions. Companies compete. Academic labs push boundaries. China leads in quantum communication. United States leads in quantum computing. Europe invests heavily in both. Quantum supremacy demonstrated by Google in 2019. A quantum computer solved a problem no classical computer could in reasonable time. Criticized, debated, but a milestone. IBM, Rigetti, IonQ, Honeywell, others building quantum computers, different technologies, superconducting qubits, trapped ions, topological qubits, photonic qubits, silicon spin qubits, each has advantages. None clearly superior. The winner isn't decided. Teleportation works, particles at the Large Hadron Collider, quarks and gluons and protons, entangled at subnucleonic scales, evidence published in physical review letters, the EPR paradox at the smallest distances ever probed, 35,000 times smaller than a proton. Entanglement is fundamental, not just for photons, for all quantum systems. Satellites entangling ground stations across oceans, quantum computers and data centers, accessible via the cloud, quantum sensors in hospitals, in mines, in gravitational wave observatories. Entanglement distributed as a utility, like electricity, like the internet. Ubiquitous, essential, invisible. Plug in, use, don't think about how it works. But it works because of experiments done decades ago by physicists testing ideas Einstein thought were absurd. Because Bell wrote an inequality. Because Clauser, Aspect, Zeilinger built experiments. Because engineers miniaturized components. Because researchers found ways to make entanglement survive in noisy environments. Because governments funded basic research with no immediate application. Because curiosity drove people to understand how the universe actually behaves, not how we think it should. 2025 is the International Year of Quantum Science and Technology, declared by UNESCO. 100 years since the development of quantum mechanics. Heisenberg's uncertainty principle, Schrödinger's equation, Dirac's relativistic quantum theory, Born's probability interpretation, Bohr's complementarity, the Copenhagen interpretation, de Broglie's matter waves, all 1920s. By 1935, the framework was established. Einstein, Podolsky, Rosen challenged it. Schrödinger named entanglement. 90 years later, entanglement is the foundation of a technological revolution. Quantum mechanics was right. Einstein's intuition was wrong. The universe is weirder than classical physics allowed. Particles genuinely don't have definite properties until measured. Entangled particles are described by a single wave function that spans space. Measuring one collapses the wave function everywhere simultaneously. No signal, no hidden variables, just quantum mechanics. Distilling entanglement, quantifying cost, reversibility under realistic operations. The idealized picture, where you can manipulate entanglement freely with no constraints beyond locality, doesn't hold. Real-world quantum computers will face fundamental limits on how efficiently they can create and use entanglement. This matters. If you can't efficiently distill high-quality entanglement from noisy states, error rates stay high. If the cost of creating entanglement is too high, algorithms become impractical. If transformations aren't reversible, resources are wasted. Understanding these limits is as important as understanding entanglement itself. You can't build a quantum computer by ignoring constraints. You have to work within them. Find algorithms and hardware that optimize entanglement use given realistic conditions. That's the engineering challenge of the next decade. Published December 2024 in Optica. These are institutions with decades of quantum research, not startups making claims, not press releases without peer review. Peer-reviewed publications in top-tier journals. Physical review letters, Nature, Optica, Nature Communications. These sources set the standard for scientific rigor. The experiments described are reproducible. The data are available. The methods are detailed. This is how science works. Incremental progress. Each experiment building on previous work. Each discovery opening new questions. Every experiment confirms it. Every attempt to explain it away fails. Bell inequalities violated. Loopholes closed. The universe operates on quantum mechanics. We've built technologies that exploit it. We'll build more. Quantum computers, quantum networks, quantum sensors, all powered by entanglement. The most absurd, counterintuitive, impossible seeming phenomenon in all of physics. Turns out to be real, essential, the key to the future. Einstein lost the argument. Quantum mechanics won. Entanglement is not only real but useful. The spooky action he dismissed is now the basis for industries, for technologies that will shape civilization. Secure communication, unbreakable encryption, computers solving problems beyond classical reach, sensors detecting signals too weak for classical instruments. All because particles interacting once remain connected forever, regardless of the distance between them. Measure one, know the other, instantly, non-locally, quantum mechanically. That's entanglement. That's how the universe works.